Okay. I said that the one phrase that I wanted you to remember from what people had mentioned during that starter question was water is polar and forms hydrogen bonds. Okay, right here. Water molecules are polar. What? Yep. See, recording. All right. One way of rephrasing the word polar is electrically lopsided. Lopsided means uneven. A molecule that is polar is a molecule that is not symmetrical electrically. Down here's water. It looks like Mickey Mouse. See? All of them. The larger of the atoms is oxygen.
Can you guys be quiet?
Yeah. Guys, get it together. And the two smaller ones are a pair of hydrogens. So you've got two hydrogens, you've got an oxygen, hence H2O. Because of the way that oxygen's electrons are spaced around the atom, it would be kind of, logical to think that you've got a hydrogen here and a hydrogen here and a big oxygen in the middle, and they would be like kind of even. But it doesn't fit that way. This is not the way it is. Instead, you've got the atoms, two hydrogens sticking off at like a 45-degree angle up off the top, and nothing sticking off down in the bottom. So that means you got more hydrogen on one side of the molecule and more oxygen on the other side. I'm guessing that from physical science you do not recall the term electronegative. Or do you? Basically, the term electronegative means it's a measure of the degree of attraction an atom has for electrons. The more electronegative something is, the more electron hungry it is. It wants to pull electrons to it more strongly than something that's very not electronegative. No, not necessarily something that becomes an anion, although that is usually true. But there's anions that aren't very electronegative. Basically, if you take the periodic table, the far top right, very electronegative. Does anybody know what forgetting helium, which is in our, what's the top right element on the periodic table?
A noble gas.
Yeah, but that's helium. So aside from helium, fluorine. Right? Fluorine is the most electronegative atom on the whole periodic table, which is why it will react with virtually anything, because almost any atom it bumps into, it will steal its electrons from it, and that constitutes a chemical bond when one atom steals the electrons from another. That's why fluorine is also very dangerous. Fluorine gas will kill you in like one breath. Chlorine is the next lower one. It will also kill you in pretty much one breath if you breathe chlorine gas. That's the reason why those things, and the next one below that, bromine. Well, nobody treats their swimming pool with fluorine because it's just too dangerous. But the next two, chlorine and bromine, that's what they put in swimming pools to kill the germs because they're so chemically reactive that anything living in there will get mangled by them as it bonds to every little bit of their cell chemistry. Oxygen isn't as bad as them, but it's up in that right corner. So those are things that attract electrons. And up in the top left corner is where you find hydrogen. It is the single least electronegative atom there is, along with stuff like lithium and sodium and things that are up in that top left corner of the periodic table. So what that means is that even though, because this is and we say we're not going to do this, but that atom is held together with a covalent bond. There is nothing in you that is held together with an ionic bond. So if you remember anything about them, don't worry about it, because the second anything that even is ionic, salt basically, gets into you, it falls apart and it's not bonded anymore, because as soon as you get something that's ionic wet, it falls apart or disassociates. So that means that covalent bonds are where two atoms share electrons. That sounds very nice and friendly. Unfortunately, sharing is not always an equal thing. Basically, think about the oxygen like somebody who's greedy, and they keep it more to themselves, and they'll let somebody else borrow them once in a while, but then they want them back again. That's oxygen. So if you figure that the electrons are orbiting from a hydrogen to the oxygen to a hydrogen to an oxygen, it's more like they go from a hydrogen to an oxygen, 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 hydrogen, oxygen, oxygen, oxygen. They stay around the oxygen more often than they do the hydrogen. What electrical charge is an electron?
Negative.
Negative. So if the negative things hang out around that atom more often, that atom is kind of negative. Not completely. It's not an ion. Don't confuse it with something that actually has, one entire extra electron and it's an ion. That's why they put this little, I know you can't see, it's the little symbol that kind of looks like that. Except it loops like over like that. It is the little, I don't even know what letter it is in Greek, but it means partial. So when you see that, this over here says like the partial negative, and this says partial positive. So you can forget the partials and we'll just deal with, so the oxygen is negative. Those two hydrogen are positive. Positive, positive, negative. Oops. Negative. Oops. There you go. So you've got all of these waters. They, in essence, are electrically lopsided. That's going to give them the characteristics of a magnet. They now have a north and south pole. And just like magnets, the opposites attract and the likes repel. So this water's oxygen is attracted to a neighboring water's hydrogen, and that water's oxygen is attracted to another neighboring water's hydrogen. And in fact, every oxygen can be attracted to two different hydrogens, and every hydrogen can be attracted to one oxygen. And so what happens is, it's sort of like you just have a bunch of bar magnets and you threw them out in a big pile, and they all kind of are stuck to each other in one big mesh. That's water. That's the reason why water has characteristics that other things don't. if you take gasoline and drip it on something, it doesn't make a little, like, droplet. It doesn't make a little dome of gasoline. It just goes, and it just flattens out to a little puddle. That's because gasoline isn't polar. None of the molecules in gasoline are attracted to each other. They have no interest in each other. They don't try and stay together. They just fall apart into a flat little pool.
Is 2 the max number of hydrogen that oxygen can?
Yes. Yeah. So, right here. Each water molecule can form hydrogen bonds with 4 neighbors, but that's because the oxygen is bonded to is attracted to 2 hydrogens, and then each hydrogen is attracted to 1 oxygen. So basically, you end up with this big, like, mesh of water molecules kind of magnetically attracted to each other. Really, magnetic is the best explanation for these kinds of bonds. If you think about, like, a refrigerator magnet, you can put it on, it stays, but you can pull it right off. Right? If you put a magnet on, like, the side of your car, as you're going down the highway, the wind will get under it and just blow it off. Right? It's not part of your car, but as long as something else stronger doesn't push on it, it'll stay stuck. Well, that's what's going on here. As long as something else stronger than the attraction isn't pushing the molecules apart, they'll stick together. But the more movement they get, the more they start to break apart. And that's what causes the different states of water. So this is what's happening. They all want to hang on to each other with this sort of, like, little positive, negative magnetic attraction. That characteristic is what causes all of the useful properties of water for living things. The first is, well, what I just said. Organisms depend on cohesion, meaning water sticking to itself. Cohesion is water sticking to other water. Co, together. There is another property of water called adhesion. That's going to be water to some other thing. Water to glass, water to paper, water to a sponge, water to wood. Right?
Could you say, like, adhesion is absorption? Or
There is no such thing as absorption. There's adhesion at the molecular level. Basically, a sponge, what you see is a sponge absorbing water. What's really happening is that the surface of the fibers that make up the sponge are getting a layer of water attracted all around them. They don't actually, in fact, it soaks into them, but what's happening is it's the water being attracted to the sponge fibers. That's the reason why you don't make a sponge out of wax paper, because it's not attracted to the wax. That's why it'll bead off. That's why you wax a car. So the only thing that makes something absorbent is it also a molecule that's polar? Is it also, like, forming bonds? So what will happen is the water will form bonds with the molecules of the whatever, the sponge or the paper towel or the... all right, so basically those first 4 can be substituted with those 2 words. Right? These bonds are weak, changing. They are always changing. This is not water molecules locked to each other. unless you're talking about ice. That's what ice is. Ice is water molecules that have formed bonds strong enough that now the water molecules don't move around anymore. Right? The reason why like water has resistance when you try and like swim or walk in water is because as you move through it, you've got to actually break these little like magnetic bonds and like part the water in front of you by popping these waters apart from each other. They don't want to let go each other, so you have to shove your way through them, which is why it's so much more resistance than air, right? Because you need to break these bonds holding them together. So that is all called cohesion, all this water sticking to each other. Down here was the adhesion. All right. If it weren't for water's property of cohesion, life could never have gone up. And it says vertical growth. Trees and other plants called vascular plants that have basically veins in them were the first ones to make use of the fact that water could be sucked up through the veins of the tree, and by sucking some of the water up, it pulls on the water down below it. So if you think about like all of the water being attached, you ever see one of those things where you've got like they put paper clips in them and they've got a magnet in the bottom, and if you pull it up, like all the paper clips are still clinging to each other, and as you pull it up, you're like dragging the paper clips up out in a big long chain. That's because they have cohesion. They're holding on to each other. If water molecules didn't do that, the plant would have to literally lift every water molecule separately. If you think about those paper clips as being like water, if they didn't cling to each other, you'd pick one up, and that's great. But it didn't lift anything else. So, like, there would be no way of carrying all the water up the tree. Because they cling to each other, if you move some of the water molecules up, they drag the rest with them, and you end up having water being able to make it to the top of a tree, or in you don't get water going up you the same as a tree. You pump it uphill with your heart. But considering plants existed before animals did, like life the way we know it, if you remember, we said that it wasn't until there was oxygen in sufficient quantities that the rest of life was possible, and trees, to make the oxygen, weren't possible without this property. So basically just you could not move water up a tree if water didn't have this characteristic of clinging to itself, which means this world would be populated by nothing but moss. That would be moss is the tallest plant that does not have any vascular tissue. That's all the higher you can get water to go if you don't have any of this like plumbing in the plant. So if water didn't cling to itself, that's how tall everything on the planet would be. It would be moss. Kind of dull. All right. So all that was the cohesion. Starting here, it's the adhesion. Oh, here's another property of cohesion. All right, surface tension. You're actually going to do this tomorrow. You're going to float some paper clips in water. You make little paper clip boats. And then you're going to sink them. Chemically. The reason why there's surface tension So if I just make all of these guys water molecules, and if these are the hydrogen bonds between them, if you notice, down and below the water, the molecules are bonded to each other in 3 dimensions, above, below, in front, behind. But once you get to the top layer of water, there is no more above. So what happens is you end up with the water molecules bonded straight sideways to the next one, which is to the straight sideways to the next one. And if you can try and picture this, this ends up creating this effect of making a trampoline out of the water. Because the water molecules on the surface are holding onto each other sideways, if something pushes down on them, they'll push down, but they'll all push down together because they're moving like a big sheet of, like, fabric, or like a trampoline cover, or whatever you call it, the mat on the trampoline. And then that means that you actually have to push your way through the surface. There's a physical, like, strength to the surface of water that once you break through that, it doesn't have that same cohesiveness below. So it's basically the strongest in terms of it being holding onto itself on the surface, which is why you have small creatures like that can take advantage of it. If you take a look at the shape of their legs, you can see that they actually have like flat feet that are laid out on the surface. They're trying to spread their body weight out. It takes a certain amount of force to push between these things and break them apart. And if you try and, put your, if those things tried to put their little legs in straight down, all their weight would be in one little spot and it would part those water molecules. But if they can lay it on the surface of them so that no one spot is pushing hard enough to break loose from the others, they can walk on water. Right? And for you, has anybody here ever jumped into water from a really tall height? Either off like the 10-meter platform, like dive platform, or off of a cliff or something like that? What did you jump off of? It was far enough for you.
Yeah.
All right. If you've ever jumped off of something that tall, you realize that when you hit the water, like, it smacks your feet. Because the problem is, those things are holding on to each other. You can only push them apart so quickly. If you go slowly and dip your hand in, it just slowly pushes them apart. They're not, they're moving slowly enough that the hydrogen bonds aren't a problem. But if you try and go too fast, the molecules simply can't get out of the way in time. And somebody falling from more than 3 stories up, water gets to be almost as hard as dirt when you hit it. If somebody's falling without a parachute, aiming for the water really won't help, because going that speed, 110 miles an hour, is like the terminal velocity of a falling human. You will basically have the same effect as hitting the concrete, because it won't get out of your way in time. And once you're under the water, it will, but not that surface layer. Yeah. If you don't land the right way, yeah. I swam in college, and we had a separate diving well there, like they do at UD, and we could feel when the divers smacked off the 10-meter board. The 10 meters, that just insanely high concrete platform. And if they did it wrong, you could feel the impact through the water, through the concrete barrier between the pools, and we was like, ooh, and you're like, oh, that hurt. And you're like, trying to, you could, oh, they'd have welts all over them, and they wore like wrestling headgear so that if they landed sideways, they didn't blow their eardrums out.
Oh my God.
Yeah, divers, they're just, you just have to be insane to do that. They're just not right.
Oh my God, that's crazy.
Okay, so, so that's surface tension. The water clings to itself. Some things can like be supported by that. It's a similar effect to if you've ever tried to walk in deep snow. Snowshoes will have the same effect for you as that insect's flat feet. It spreads your body weight out and you won't sink in. Right? Same with skis. If you've ever been skiing in deep snow and you lose a ski, you have to pop the other one off to go get it, and you like step off your ski and you're like, you like sink up to here because now you don't have all your weights in too small of a spot and you end up like pushing the snow down. Okay, that's cute and all, surface tension. And while there's a few insects that do rely on that to walk on the surface of the water, it's not life-changing. This is life-changing. If it weren't for water, this planet would not be habitable. Water stabilizes the temperature of the planet. That's the reason, the moon is just about as far away from the sun as we are. At times when it's beyond us, it's further. At times when it's closer, but it's pretty much right here. During the day, the moon is like 250 degrees on the sunny side and like minus 300 on the shady side. Like night and day have like a 500 degree swing because there's nothing to hold the heat. Rock doesn't do a very good job at holding the heat. It warms up real fast and it cools back down real fast again. Water doesn't. If you go to the beach in late September, it might be 50 degrees out, but the water is still like 68 degrees in the ocean because it takes a lot longer for the ocean to cool down, not because of its mass. Like the ground gets cold, well, that's the mass of the earth. So it's not a matter of, oh, there's lots of water, it takes a while to cool down. Well, yeah, there was a lot of earth under you, but it didn't seem to be a problem for the sidewalk to get cold. This is the most important characteristic of water in terms of life existing on the planet. Okay, so it absorbs heat from warmer air and it releases it in colder air. Basically, water can hold a lot of heat. Heat is not the same thing as temperature. Take a look right here. Temperature versus heat. Temperature is what you measure on a thermometer. There is no thermometer for heat. Heat is an amount of energy that something has. For water, for most things, it's how fast its molecules are moving. Steam is water that is moving really fast. You can actually see it move. It goes up and flies through the air as steam. And it's literally like rising up out of the boiling water on your stove and taking off into the air. The molecules are going so fast, like the heat from the stove has made them vibrate so fast, they break loose from each other. Those little hydrogen bonds aren't strong enough to hold them together because they're all vibrating too fast until they break loose and take off on their own. And that's what creates temperature. The fast-moving molecules create the temperature, but the molecules moving fast is actually their heat. But the thing is, water holds a lot more heat than anything else does. Because if you think about it, how fast the molecules move is their heat. But these molecules are holding on to each other. They resist moving. So if you warm up water, the molecules cling to each other and don't want to let go. And until they start moving fast, the temperature won't go up. So you can add heat to water. You can put water on the stove. And I mean, if you put your hand on the stovetop for 30 seconds, I'm sure you won't have any skin on the front side of your hand. That much heat is being delivered to the water. But in 30 seconds, you put your hand in the pot, it's barely even noticeably warm. It took in enough heat to burn the skin off of you and just made it disappear in the water. Because what it did was, it made the molecules start to vibrate a little, but not enough that they broke loose. So you have to add more heat and more heat, and it's not until they finally break loose from each other that they actually have the temperature go up. Because it takes a lot of energy to break those bonds to begin with, until you get them to start coming loose and moving around on their own, they take in heat and take in heat and take in heat, and the temperature hardly goes up because most of the heat is being used to break the bonds, not actually make the molecules move around. It's sort of like, if you've got, if you got a bunch of balls that you're trying to hit with a bat and make them scatter all over the place, except that they're glued together. First you have to beat on it for a while to just break them apart. Then once you break them apart, then you can make them go flying. But the fact that they're clinging together means a whole lot of beating goes on and nothing's happening. Yes, you're delivering energy to it, but nothing is resulting from it because it takes enough energy of you beating on it to break the pieces into individual balls that then will go flying when you hit them. That's the idea. Right? The energy in the form of the heat from your stove is basically beating on the water molecules, and they're not coming apart right away. And so they can suck up a lot of heat and not change and not increase in temperature a lot. So the high heat that would have burned you from the stove basically just gets sucked up into the water, and the water does not increase its temperature much, which means you took a lot of heat and turned it into only a little heat. You managed to suck up the heat so that, even the air above the stove gets hot, but the water doesn't. So you're actually taking heat that would have warmed up everything else and literally sucked it up so that it wasn't available to heat up anything. And that's the reason it's always cooler near water. On a hot day, it's always cooler near water of some sort, whether that's a pool or a lake, or even just having a sprinkler going in the yard, or having I know sometimes at sports events they'll have these misters that just spray mist of water into the air. It's not for you to walk through it, although you can, but it's actually cooling the air down. It's also the reason why it's always cooler near trees, not necessarily under trees. Yeah, I know under trees are in the shade. Being near trees will make the air cooler because the trees suck water up out of the ground and they give off water from their leaves, and the water vapor coming out of their leaves sucks up the heat in the air, and it's always cooler near trees, like I said, not under them. But that property is the only thing that keeps us from baking during the day. And then the heat that was absorbed during the day gets released from the water slowly at night, so that we never heat up too much in the daytime and we never cool off too much in night. It takes the length of seasons for us to actually change the temperature of the air that much. And you need months of cooling and cooling until you end up getting freezing temperatures. This is the measure of you beating the balls with a baseball bat. A calorie is how much energy it takes to heat up 1 gram of water 1 degree Celsius. So a kilocalorie is the amount of temperature energy needed to raise 1,000 grams of water 1 degree Celsius. This is a food calorie. If you ever read the packaging, calorie is spelled with a capital C when they're talking about food, because it's the convention of food companies to use kilocalories as their measure, because nobody wants to buy a candy bar that's 370,000 calories, but that's what they are. A can of soda is 250,000 calories. It's just depressing if you look at it that way. So they're telling you that it's only 250 kilocalories. Right? They're telling you it's 250 thousands of calories, 250 kilocalories.
So when you're on those treadmills, they tell you burn like 25 calories?
No, they're telling you kilocalories as well. So the thing is, your body doesn't burn, like 1 calorie in you is not enough energy to do, 1 gram of water is basically, like, I don't know, it's like 12 drops of water. You're a lot bigger than that. You've got a lot of water in you. Right? But, I just didn't want you to think that, like, because if somebody actually thinks and does the math, that means that, well, the calories in your food wouldn't mean much. Yes, because a calorie is a calorie is 1/1000th of a food calorie. So, I'm just saying, this is the way you describe it in chemistry. So if you're doing a chemistry problem, they use calories, little c, which just means to raise 1 gram of water 1 degree Celsius. But as soon as you talk about living things or food or the energy expended by exercise, then you're talking kilocalories. We're too big to talk about in calories. All right, the word specific heat is the word for how much beating it takes to knock the balls apart and make them go flying. I said a calorie was how much, it was a measure of the energy that you use, but every substance has its own clinginess. Every substance either takes a lot of energy to break the things apart or almost none. Water has one of the highest specific heats, meaning it takes more energy to break water molecules apart than to break almost any other molecules of any other substance apart and get them moving, which is why almost everything else heats up faster. Which do you think has a higher specific heat, plastic or metal?
Plastic? Oh, okay.
They're both the same.
Specific heat is the way of measuring basically how much heat it takes to warm that thing up. A high specific heat means it takes lots of heat to warm it up. So which has a higher specific heat, plastic or metal?
Warm it up to what?
Anything. Just make it get warmer. Which is harder to warm up?
Plastic.
Higher specific heat. Metal has a lower specific heat. It takes less energy to heat up metal than it does to heat up plastic. That's why the things you insulate stuff with, like styrofoam, that's got a ludicrously high specific heat until you catch it on fire and then it just burns. But that's the reason why it insulates, because the heat from the outside. By the way, did you know cold's not a thing? Cold. Heat is a thing. Cold is not a thing. There is no such thing as cold. You don't get cold. You lose heat. Like, if you put ice in a drink, the drink does not get cold. Cold does not spread from the ice cube to the drink. It takes away the heat. Cold is simply the absence of heat. So, like, when you're outside in the winter, if you don't have enough layers on and the cold kind of like penetrates through your jacket and the cold is not like soaking into you, you're like losing your heat, and the heat on the outside is gone first, and so you start losing the heat further and further into your clothes until it's finally you're losing the heat directly off your skin, and that's when you start feeling cold. But you don't get cold, you lose heat. So basically, that's everything I just said.
And just like when if you're wearing a jacket, it doesn't keep the cold from coming in, but it keeps the heat from.
It keeps the heat from going out. Right? So anything that insulates you is something that keeps the heat in and won't let it spread by making it hard for obviously you don't wear tinfoil clothing because it has a very low specific heat. Your body will heat up the tinfoil really fast and it will just go right into the air. That's probably a good way to cool you off, but not a good way to keep you warm. Does anybody know what's got the highest specific heat?
Water.
It's the most efficient insulation, and you only usually use it in containers that hold liquid.
Plastic?
Would it be a
Silver? It's not.
An actual real brand name thermos uses it.
Thermostat. It's
like I didn't know that was an actual.
You can also buy glassware, really expensive. It's like Bocar or something like that.
Stuff. What is it? That looks like.
A vacuum. You can buy double-walled glass, like coffee cups, but a thermos works because it's got an outside layer and then it's got an inside layer. You put your drink in here, and in between the two is nothing. They suck a vacuum out, they suck all the air out, so there's nothing to warm up. There's no molecules to transfer the heat, and only radiant heat, which would be sunlight shining through it, would have heat going through it, but nothing actually warming it up inside. There's nothing, there's no connection between the two, so almost none of the heat leaves, which is why, that work, a coffee, one of those, travel mugs, those usually just have, foam in them or something. But you can buy ones that are actual double-walled vacuum thermoses, and they'll keep something hot all day long because the heat has no way of getting across that gap. Right? But you know, obviously it's very difficult to make a vacuum work for a living thing. All right, we stop.